This is Jimmy. He's a pendulum. And a gingerbread man. There's a problem with Jimmy, isn't there?
Because Jimmy doesn't Jimmy, Jimmy Bob's, and Bobby isn't Jimmy, and Jimmy isn't Bobby.
So the question really is, Gwen, the real question that keeps my head rattling the biscuit tin at night, is should we rename Jimmy Bob? Or call him Bobby Jim?
Or Jimmy Bob?
Or should we talk about the energy stored when he's doing this sort of thing?
I think the only solution is the latter. We're going to have to talk about the energies.
I think we are. So I'm going to put Jimmy over there. Or Bobby Jim. Into a box, and that was quite exciting.
So the energies of a pendulum as it goes from side to side is what this video is about.
Yeah.
So first we draw ourselves a pendulum.
That's a very lovely pendulum there.
Thank you. I'm not quite as pro as you at drawing
Oh,
pendulums.
that's okay, Wayne. Practice makes perfect. So a pendulum moves from there to there is one full oscillation. So that the time it takes to do that would be the period.
Yep. So if we call that T, because this is a time axis.
Yeah.
This is against energy.
Yeah.
So what energies have we got in this pendulum truth?
Well, that's a good question, Wayne. There is kinetic energy when it's actually moving, and potential energy, which is throughout, but here it is not moving when it in fact reaches its highest displacement, but has a lot of potential energy, and the opposite is here. And yes, it's best displayed with the graph.
So we're going to have a half period as well.
Yeah.
And that's when it's going to get to the other side. So we'll talk about gravitational potential energy first.
Yeah.
So it starts at maximum, as Trip just said.
Yeah, and as it gets to here, it's going to 0.
And then when it gets back up again, that will be the half T. It's going to be back at the maximum, and as Trip
So actually fall quite steeply here, and then go back up to the maximum at half T, and then repeat to the other half.
Exactly, just like that.
But and that was our potential energy, should we label that?
Yep. So red is the gravitational potential energy. Now I've got red again somehow, haven't I? Kinetic energy for the blue.
Yeah. So our kinetic energy is the opposite, really, because that's when it's moving, and it's changing. The thing that affects that is its velocity. Now I mentioned in the last video that Vmax occurs at the bottom. And if Vmax occurs at the bottom, so must the maximum kinetic energy. So that's why it happens to be the opposite of our potential, because it's 0 when it gets there, because it stops moving, max when it gets there, and then repeat.
So kinetic energy.
And
so
this isn't,
we can then sum up as a total energy of the overall system by simply adding the things.
And if you do that, you from AS, it just becomes a line.
It neatly goes across the top, just like that, and that's your total energy.
Now, there's two equations of working that out. One is for when you are in a gravitational situation like this, and you also have situations in springs where you use elastic potential instead.
Now both of these are from your AS, but slightly different. Your gravitational potential energy, so we'll call it GPE.
Yeah, remember it being mgh, but when we're talking about harmonic motion, our distance is always just called x.
Yep, so it's just our displacement from the equilibrium position rather than h. And that's the only difference, and that's from AS.
And our elasticity is exactly the same, and that is just half k squared.
K changes for different materials.
Yeah.
You don't need to worry about that. You just need that's in your formula booklet and from AS. You just apply it as usual.
Yeah.
Where x is a displacement from the equilibrium point.
And that's the energy.
Next, we're going to go on to damping resonance.
Yeah. That damping resonance, and that is the end of circular motion, I think.
Yeah. So that's cool.
That's pretty cool.
We should definitely go to Harmonic Motion's gig then, right?
Yeah, definitely.